Right, so we've got a piston here attached to a light spring. Okay, the spring we're given the modulus of elasticity, 625 newtons, and the natural length of the spring is 0.2 meters. Okay, so what happens is that this piston compresses the spring. Okay, so it's held here at A to start with, so that the distance between A and B is 0.1 meters. Okay, so if the natural length is 0.2 meters, you can see it's being compressed, so in effect it's been halved in length, hasn't it? So the x value here, okay, which we think of as the extension, yeah, but it can also be a compression, will also be 0.1, okay, because it's gone from 0.2 to 0.1. So in part A then, they ask us to calculate the elastic energy stored in the spring. So remember, the elastic potential energy, okay, is given by this formula, so lambda x squared over 2L, twice the natural length. So we know the lambda is 625, okay. The extension is, or the compression is 0.1, so we square that, and we divide that then by twice the natural length. So natural length, remember, of the spring is 0.2, okay. So we go about to work that out on our calculator, and I get 15.625 joules. So that measures the energy that's in the spring, okay, at the start. It then gets released, okay, and obviously because it's been compressed, it'll expand then in length, okay, and we're asked to find the speed of it at C, okay, when it is of length 0.2 meters, okay. Now, if you think about it, it's at its natural length then, yeah, because 0.2 meters is the actual length of the spring, as it says there, yeah, the spring's at its natural length, so the compression then, or the extension, will be 0, okay, so it's important to sort of see that there. However now, right, we've also got a resistance to motion of magnitude 46 newtons, okay, so I put that force in there, so as it travels from A to C, okay, that distance of what, 0.1 meters, it's got a resistance there. So that means, okay, when we start B up, we simply say that the energy is not conserved, okay, right, there's been a loss in energy. Okay, so it's important to note that. So what we'll do then is we'll use the work energy principle, okay, so that we can equate them. So let's consider the energy then to start with, okay, so I'll write that in, the energy at A, okay, well, if we think about it at A, the only energy that's there is the energy that's stored up in the spring, the elastic potential energy. It's got no movement because it's at rest, so the only energy will be the elastic potential energy, yeah? I mean, you know, it's good to actually write down all the different types of energy, so you could have potential energy, kinetic energy, but in this case, the elastic potential energy will be what we calculated in A, okay, the energy that's stored up in the spring. Potential energy is 0, okay, because this is happening on one sort of level, okay, in a sort of horizontal plane, so we don't have to worry about potential energy there, and kinetic energy, of course, is 0 to start because it's at rest. So the total energy at A is 15.625. When we then consider the energy at B, okay, not B, sorry, at C, yeah, let me change that. Well, we've got kinetic energy. I mean, let's just write all these down. Elastic potential energy plus potential energy plus kinetic energy. Well, at C, because it's at its natural length, yeah, the extension is 0. Of course, the elastic potential energy is 0. There's no energy stored up in that spring because it's at its natural length. Potential energy is 0, as we already discussed, because it's all happening on the horizontal. Kinetic energy then will of course be half mv squared, okay, so the mass is what is it, 0.8, so you end up having 0.4 v squared, okay. Now, because energy is not conserved, we cannot say that these are equal, okay. There is work that's been done here, okay, so we need to consider that. So let's consider the work done by the resistance, okay. So the work done by the resistance would be the energy that's been lost. Okay, so remember the work done formula is force times distance, yeah? Well, the force in this case is a constant 46 newtons. The distance the spring has travelled in that time, or the piston rather has travelled in that time, will be 0.1 meters. Yeah. So if I work that out, I get obviously then 4.6 joules. So in a sense, there's been a loss in energy of 4.6 joules. Yeah. Okay, because there's been a resistance to motion. So what I can say then is I can write down the work energy principle. Okay, so I can say, yeah, the energy at C, well, it's not quite equal to the energy at A, isn't it? Okay, we can't say that because energy is not conserved. But what I can do, I can take away the energy I had at A, due to the energy that was stored up in the spring. I can take away the work that's been done, okay? The work that's been done by the resistance. So the energy at C then, well, we know is 0.4 V squared. The energy at A is 15.625, the energy stored up in the spring, and the work done by resistance is 4.6. So it's just a little bit of algebra that we've got to do, okay? And we can work out then what V is. So if I do 15.625, take away 4.6, so I get then 0.4 V squared is 11.025. V squared then, well, if I divide by 0.4, I get 27.5625, and then of course I've got a square root then, and that comes out to be 5.25 meters per second.